Well, the last feature today is a video presentation which was written, produced, and directed by Stone and Webster, using students here at our high school 2 years ago. And the gentleman who plays the teacher is a professional actor. This runs about 12 minutes. I hope you enjoy it.
Good morning, class. Let's settle down and get comfortable. We have a lot to cover today. Now, this light, as you know, comes to us through electricity. Only in this case, the electricity comes to us in a new way. It isn't at the switch or the receptacle or the plug or any different. It's just that this school is part of an experiment designed to reduce our dependence on resources which are becoming scarce. Electricity is the cleanest, most flexible power we know of, and we do use a lot of it. As a matter of fact, in the last 25 years, our use of electricity has increased 5-fold. So it now represents about 1/3 of all the energy used in America today. Now, how do we produce this electricity? Well, we produce electricity through a series of energy conversions by using heat energy to change water to steam. The heat energy is converted to mechanical energy in a turbine. A generator converts mechanical energy to electricity. Simply, we use gas, oil, coal, hydro, and nuclear to make electricity. And we're presently heavily dependent on non-renewable sources of energy, fossil fuels. And in the past, we've had lots of oil to burn. And this has contributed significantly to our conversion from a basically agricultural society to a mostly industrial society. As a result, we've been the world's largest oil producer and the world's largest consumer. As both industry and population grew, we soon outgrew our capability to produce all the oil we needed to support our standard of living. Now we import almost half of our oil. Our finite supplies will become exhausted. Oil and gas in a matter of decades, coal in a few hundred years. Okay, so what do we do? Yeah.
We have to develop alternative sources of renewable energy.
First as a supplement, then as a replacement. Okay, what is energy?
The flow of electrons.
All right.
A form of power.
Okay.
Motion.
Motion, sure. Those are all partially correct. But the formal description of energy is the actual or potential capacity to do work. Got that down, okay? Now, as this book is sitting here, it isn't got any energy at all. It isn't doing anything. But if I lift it up, I'm giving it energy. And as I drop it, the noise that results is the result of the energy I've given it. Okay, much of our energy comes ultimately from the sun. The organic fuel supplies we have depended on so much, wood, oil, natural gas, coal, are all indirectly stored forms of solar energy from the prehistoric past. The vegetable and animal life that formed the coal and oil used the energy of the sun to convert chemicals and minerals into organic matter. Every day, 85 trillion kilowatts of radiation strike the Earth's surface. Each year, the United States receives solar energy equivalent to that contained in 1,150 billion tons of coal. So if we can develop means of harnessing this solar energy, we can begin to find an answer to our energy demands. So now we come to the experiment. We're experimenting with photovoltaics, allowing the direct conversion of sunlight into electricity. What we're actually doing is rediscovering some age-old processes and devices. We're certainly not the first to have looked at the sun. It's been worshipped since the beginning of time, for life is truly created and nurtured by it. Now, the Aztecs believed they were the chosen people of the sun. Their calendar was an elaborate representation of what they believed to be the most precious thing in the universe. Human sacrifices were offered for its continued blessing. Well, along with the mysteries of religion and mythology are clear, planned applications of this star's energy. More than 2,000 years ago in ancient Greece, Socrates described the design and layout of houses which would maximize solar heating of a building during winter. His plans detailed the slopes of roofs and placement of windows to provide heat in the winter and protection in the summer. The Greeks were not alone in their observations, though. Most human cultures sought to incorporate the use of the sun's energy into the design of their architecture. Well, the baths at Pompeii are an example of the solar water heating used by the Romans. Channels carrying water to the baths were built open to the sun and lined with grooved black slate. The slate was heated by the sun, which in turn heated the water as it ran along the grooves on its way to the bathers. In the American Southwest, the Indians relied upon the sun to keep their homes comfortable year-round. This passive solar design oriented the buildings with main rooms facing south. The south wall absorbed sunlight during the day, and at night the absorbed heat was released into the house. Our ancestors knew of other ways to harness solar energy besides the orientation of buildings. The Greeks, Romans, and Chinese all experimented with mirrors that could concentrate the sun's rays with enough intensity to cause fires. There were those who sought to direct this new capability for military aims, but there were others who could imagine its peaceful uses. Leonardo da Vinci proposed the construction of a mirror that would concentrate the sun, producing heat and power for industry and recreation. It would be a parabolic mirror 4 miles across that would, as he put it, quote, supply heat for any boiler in a dyeing factory, and with this, a pool can be warmed up because there will always be boiling water. Not until the following century, during the Industrial Revolution, would the dream of Da Vinci and others of using mirrors to produce solar power be revived and realized. A French mathematician, Augustin Mouchat, was concerned about France's need to import almost all of her coal in 1860. Well, with the intentions of reaping the rays of the sun, he embarked upon decades of pioneering research. He developed a steam engine powered by the sun, which was tested and used in Algeria for pumping water. His machines were displayed at the Universal Exposition in Paris in 1878. Well, Americans at this time were also voicing hope that solar energy could be used for the machines of the industrial age. Captain John Erickson, a designer and inventor, was aware of Mouchat's work, and he set about designing his own solar motor, using a concentrating mirror, a boiler, and a steam engine. Then in 1892, an English inventor living in Massachusetts, Aubrey Aeneas, founded the Solar Motor Company of Boston to design and manufacture commercial solar engines. After a number of setbacks and some promising results, he put his final design to work in Arizona, where it pumped 1,500 gallons of water per minute to irrigate farmland. In 1907, an engineer named Frank Schumann in Tacony, Pennsylvania, was developing a solar collector of mirrored sheet metal troughs reflecting heat onto boilers. Built to operate under cleaner conditions than the smoke-filled skies of Tacony, Schumann took his power plant to Miadi, which is a suburb of Cairo, Egypt. The solar steam plant turned sunshine into work. Well, there was resentment for this automation, which would do away with the need for manual laborers. Well, with the additional confusion caused by World War I, the plant was eventually abandoned. Well, during the next 20 years, the idea of solar applications was kept alive. In fact, it was pretty commonplace to see solar heaters in California, Arizona, and Florida. But during the 1930s and 40s, some things happened which put solar research to rest for a while. You see, one of the main components of solar heaters of the time was the copper used for the piping. And during World War II, the price of copper and other materials skyrocketed because of their strategic use. The country's energies were directed towards the war effort and not much else. At the same time, huge discoveries of natural gas and oil were made in California. The cost of energy plummeted, and electric water heaters became very attractive. Society was becoming dependent on the newly found fuels to provide the energy it needed. Today, the U.S., with 5.5% of the world's population, is consuming more than 31% of the world's energy. Translated into oil, that's about 60 barrels a year per person. Since we can no longer afford this excess, we must develop a new energy source. Our hope lies in the fact that we can make electricity from different fuels. This development will be difficult and time-consuming. Reinventing the wheel is an occupational hazard of science. The solar energy field has had its share of fits and starts, but the spark of experimentation has never quite flickered out. In 1839, Edmond Becquerel, a French experimental physicist, discovered that sunlight caused an electric current to flow in certain materials. 50 years later, Charles Fitts made a solar cell which could harness this photovoltaic effect, direct conversion of sunlight into electricity. This prototype was not very efficient and did not attract much interest. In 1954, Bell Laboratories made an accidental discovery that revolutionized solar cell technology. Their breakthroughs in transistor technology made the cells which we're using here today possible. They function with no moving parts, no fluid, or consumption of material. Now, most solar cells on the market today are made of silicon, which is found in ordinary sand and is the second most abundant material on Earth. One silicon atom has a nucleus of 14 protons and 14 neutrons, with 14 electrons in orbit around the nucleus. Now, electrons are what make electricity, since a flow of electrons is an electrical current. Manufacture of a solar cell begins with a cylindrical crystal of nearly pure silicon, which is cut into very thin wafers of crystal. Two different materials are infused into the silicon. One surface has a small concentration of impurity added to it to make it capable of conducting positive charges. It becomes P-type silicon. The rest of the wafer has been treated to conduct negative charges and is therefore called N-type silicon. Sunlight penetrates the wafer, reaching the area where the two different types meet, the P-N junction. Some of the sun's energy is transferred to some of the electrons, giving them enough energy to escape the atom, leaving a hole. Holes represent a positive charge and therefore attract the loose electrons. Since silicon is a poor conductor, these loose electrons are conducted more easily in the external circuit, ultimately filling the holes. If a light bulb were attached in the circuit, it would light up. These silicon solar cells are a necessary part of the power supply system of most spacecraft. It started with Vanguard 1, our first space vehicle. Skylab had extendable solar panels that produced kilowatts of electricity, powering a variety of instruments aboard. The cells at this site are connected in series within modules to raise the voltage to a usable level. The modules are connected in parallel to increase the current. The whole array generates 100 kilowatts of electricity. We used to get all our electricity from the power lines. Now we get some from photovoltaics and the rest from the utility. And since this is an experiment, a number of variables will be monitored to evaluate the efficiency and economics of this system. We'll be determining how much power is generated under different conditions, seasonal changes, cloudy days. The tilt of the panels will be adjusted in order to find the best position for optimum sunlight exposure. A weather station will be used to make correlations between atmospheric conditions and electrical output. Studies will be made of direct and indirect components of insolation. Insolation is the amount of sunlight that falls on the surface of the Earth. Direct insolation is the amount of sunlight falling directly on the Earth's surface. And indirect insolation is the amount of sunlight which is dispersed and reflected from clouds and the atmosphere before reaching the Earth's surface. Experiments such as these are expanding our database, making our energy strategy more effective. Well, we're acquiring information from this facility that will help design future larger-scale photovoltaic systems. Beverly is already a part of history, but it's becoming clear that solar energy has a significant place in the future. New technologies are being developed and coordinated into national energy policies benefiting society. Its time is coming, and there's nothing quite so powerful as an idea whose time has come.